My name is Andrew Maas. I just finished my PhD here at Stanford. I was advised by Andrew Ng and Dan Jurowski. I worked on deep learning for speech and text. So lots of stuff relevant to this class, except I was more on the speech side than probably most of the work you've done so far in the class. So today I'm going to talk about how we use deep learning, particularly for speech recognition. So far in this class, you've focused, I think, a lot on sort of language understanding. And from my perspective, I want to first transcribe what someone is saying, and then pass it to the systems that you've been building so far that understand sort of people's intent or how to answer questions based off of whatever query comes in. And this is a talk I normally give for speech people who don't know neural nets. And so if I'm assuming that you know something about speech that you don't, please feel free to just stop me and ask questions. Because there's lots of background. Oh, and also this will slightly overrepresent my work because I didn't go out and make slides for everything else in the deep learning for speech field. I think there's a lot of other people's results, but this is not a unbiased view of the deep learning for speech world.
Do you mind moving your mic up a couple inches?
Up, okay. Try it there. Okay. So first I'll go into an overview of what a speech recognition system is, roughly how they work from a high level. So speech recognition systems are really, really big and complicated, at least traditional systems are, relative to a lot of other places where deep learning is applied. So for example, in computer vision and some of the text processing pipelines that you've seen in the class so far, a speech recognition system is just a lot of code. And the reason for that is mostly historical, and we're starting with the advent of neural networks getting really high performance results to be able to replace a lot of that complex stuff with much simpler machine learning driven systems. So I'll give you an overview of how speech recognition systems work today, like how Android and Apple run your voice, and how neural nets come into play are these things called HMM DNNs. I'll explain what those are. So that was the big advance in speech recognition system over the past, I guess, 6 or 7 years now. So now all of your actual devices are probably using neural networks, especially if they're connected to a cloud-based ASR, automatic speech recognition system. So I'll go into sort of how neural nets have made a really big impact in those systems, and then finally some very recent work on how we might be able to replace these very complicated HMM DNN systems with really simple, essentially doing speech recognition with 2 neural networks. And I think that's kind of the future of speech. So overview, so what is speech recognition as a task, right? We all carry around these phones. These phones that you have in your pocket have actually really, really impressive microphones on them. Usually there's noise cancellation. They're oftentimes connected to the internet, so we have kind of unlimited computation if we're willing to suffer some latency. And yet the main way we interact with these phones is we kind of poke at them, and it's really distracting, and we crash our cars or we crash our bikes or whatever. That's bad. So, oh shoot. Give me just a second. It's playing automatically, I think. Maybe not. All right. So we start with a phone, right? We talk to the phone. We get from that this thing called a spectrogram. This is just a different way of representing the waveform that comes off of your microphone. So this axis is frequency, this axis is time. I'm showing you frequency over time. This thing is messed up, sorry. There. Okay, So we get our features. Typically, there's some pre-processing I need to do just purely from a signal processing perspective. And that's things like remove echo or remove background noise, those types of things. And then I need to transcribe that, so I need to convert this waveform into these symbols that we call words that are really pretty distantly removed from the actual waveform that comes out of our mouth. So this is a really complex task because there's lots of structure in text that we don't necessarily respect in language and is not always obvious because as we just sort of continuously speak, we do not speak in clean written text. And once we have our transcription, we want to pass it on to some understanding system. And this understanding component you guys have talked a lot about in the class so far, I think. So things like question answering, paraphrase detection, search query understanding, or in speech, another big one is dialogue systems. So I want an agent that's going to understand what you say and pick an action to take in response to that. So are you trying to book airline tickets? Are you looking for a restaurant? Those types of things. So in contrast to standard computer vision, this pipeline is significantly more complex, I think, because of the output representations that we care about. So in computer vision, we're given a bunch of pixels, which is not all that different from our spectrogram. But usually the mapping is a little bit more direct to sort of formalize. So I can apply a deep neural network or a convolutional deep neural network, and I can do things like give you a bounding box for a cat, and I can give you a bounding box for clothes, and maybe I might be able to do things like classify actions, like this is a cat climbing, something like that. In speech, because our output representations are natural language, it's more difficult than just sort of declaring here are labels and here are bounding boxes, because as you've seen with things like language models, speech has language has lots and lots of structure, and therefore this signal to output problem isn't so easy as just something like classification. So that's great. It makes it really interesting because you have these really complex sort of overall pipelines you have to deal with, and getting deep neural nets to interact with the rest of the system is a very interesting problem in and of itself, but it also makes it much more difficult to make progress in some sense. So for this talk, I'm going to focus on transcription. That's one component of the system, and I'm going to mostly ignore the rest of this language understanding pipeline. Cool. So what does speech data sound like? The hardest version of the problem, or one of the hardest versions of the problem, is conversational speech. So in terms of data, there's sort of different levels of complexity. So the simplest level of complexity is things like a digit recognizer, where it's a person who knows they're talking to a machine, and they only want to say things like zip codes. Then it's very easy, because the person is not necessarily speaking naturally, and they're speaking from a very restricted set. So on kind of the opposite end of the spectrum is people talking to other people because they don't try to sort of speak in a easy to understand way. So here's an example of one of the data sets that we use for people talking to other people.
But it was really nice to get back with a telephone in the city and everything.
And it's safe to sleep.
Yeah.
I could never sleep when I can't sleep.
Well, the only way I could bear it was to be asleep. I was like, well, it's not going to get over until, you know.
Because of the rain.
Yeah, really, I think that's what ruined it for us.
That is true.
Okay, so if we listen to that again and now look, so these are the transcriptions that a professional transcriptionist provides to us, and you'll see they're being very careful to transcribe things like fragments. And also, if you just read this text, this is not text that you would probably send someone in an email. There's lots of ums, there's lots of repetitions, right? You know, and I think he restarts part of a sentence.
But it was really nice to get back with a telephone in the city and everything, and, you know. Yeah. Well, the only way I could bear it was to be asleep. I was like, well, it's not going to get over until, you know. Yeah, really, I think that's what ruined it for us.
Yeah, so if we were going to take this raw transcript and convert it into an email that we would actually want to send someone, we'd have to do a whole bunch of language understanding afterward to kind of post hoc fix all of these errors. And so that's what makes kind of what we call conversational speech different from things like dictation, where I know that I'm dictating an email and I'm trying to sort of speak in emailese rather than actual just kind of conversational English. So just to give you a sense for a data set, so one of the most standard data sets that we use is about 300 hours of these types of conversations. So two strangers, the automated system calls them, they talk to each other about a topic that the automated system shows for them. They haven't met before, and so it's kind of just like an awkward first phone conversation on a topic between two people. We have about 5,000 speakers and about 300 hours. So in the probably like 5 years ago, what made speech really interesting from a deep learning perspective is kind of before people were able to use neural nets on ImageNet, speech was one of the places where you had a whole lot of labeled data. And I'll show you how we get those labels in a second. But it made it very different from when people were doing kind of lots and lots of unsupervised pre-training for the neural nets and then fine-tuning with a tiny bit of labeled data. Speech was a domain where we had lots and lots of labeled data. And so it was very interesting from a machine learning perspective. So now let's talk about, given that type of data, how does a speech recognition work? And so traditional speech recognition systems, first you start with a bunch of linguistic assumptions. And those linguistic assumptions revolve mostly around how words are pronounced. So we have words, we know what words are. The next level down from words, or 2 levels down, because you have syllables in between, is phonemes. So in English, there are about 44 phones or something like that, depending on how you count. If you look across all possible phones, it's something on the order of like 80 or something like that, but that includes really, really rare ones like clicks and like inverted plosives. So like you say G, but it's while you inhale, so it's like so like there's lots of weird phones. In English, we only use 40 or so of them. But so we have a resource which is telling us pronunciations. So English is particularly tricky, and you have to rely on these external resources because the orthography of English is not very good. So orthography means, given a word, can you tell me how it's supposed to be pronounced? And because English is kind of amalgamated from many different root languages, English has really terrible orthography. Other languages, so Spanish, for example, has very good orthography. If I show you a written word in Spanish and you're a speaker of Spanish, it's very, very likely that you'll be able to pronounce it correctly. So we use our pronunciation dictionary, break our word into phonemes, but it turns out that phonemes are not they're not significantly distinguishable because so if we look at an audio form, this is me saying the word Samson. So S, A, M, S, O, N. What happens is that the phones bleed over. So the fact that I'm saying an S before this vowel impacts both the end of this S and the beginning of this vowel. And so rather than using just our 44 phonemes, we break our system, or we break those phonemes into a set of somewhere around 10,000 states. And what those states are, we start by taking triphones. So rather than treating AE as a single unit, that's kind of a base unit, we treat S followed by AE followed by M as a base unit. And so that's what we call a triphone. And then because we can't deal with 44 cubed things, we do some sharing of the states. And so we end up with something around 10,000 of these shared triphone states. In better systems, you'll use larger contexts. So like the IBM system uses Quinn phones. So you're looking at the base phone plus minus 2 phones of context there. And so now we have a sequence of states, and we use an HMM to enforce constraints about what state we're allowed to be in at any given time. So the transition probabilities of an HMM are encoding the constraints that because these things have context, I can't jump from one to the other arbitrarily. So if I was just in a state that says I must be followed by an M, then whatever the next state I see is, it better have M as its base phone. And that's our transition matrix of our HMM. And the other part of an HMM is your observation model. So traditional speech systems up until about like 5 years ago, these were done with Gaussian mixture models. And the idea behind that is basically that Gaussian mixture models, it's very easy to do learning in them because you're basically just counting things to get the sufficient statistics for your Gaussians. And if you have a lot of data, Gaussian mixture models are kind of reasonable density estimators. So they give you a reasonable distribution P of x given S, where x is what features are and S is your state. So it's a generative model of if I'm in this state, I should be observing features that look something like this probability distribution. Does this make sense? Any questions about this framework? Good. The big change, why I'm talking in this class, is because it turns out if you rip out your Gaussian mixture models and replace them with neural nets, your system just categorically improves in almost any case where you have non-trivial amounts of training data. So how does that work? So a deep neural net you guys are all familiar with by now. So instead of having a generative model, so instead of modeling P of x given S, we use a DNN to model the opposite, which is we use a DNN to just classify which state are you in given the acoustic features that you observe. And DNN, just a softmax classifier, gives us a distribution over those states. And then using kind of stupid little normalization trick, I can get something that looks like a P of x given S score. The trick here is that there's some, so P of S, P of X, I don't have a good estimate for because P of X is like a model over what audio is supposed to look like in the whole world. But because X is fixed for this entire utterance, it doesn't matter. And so if I'm just looking to figure out which transcription is the correct transcription, X is a constant, and so I don't care. So yeah, this is what made everyone's speech recognition error rates go down by somewhere between like 10 to 20% relative, starting around 2011. So the initial work was by George Dao, Li Dang, and Dong Yu and Jeff Hinton at MSR. And they showed, yes, this works really well. And probably within 2 years, every other major speech recognition company was using deep neural nets instead of mixture models in production. So like Google switched probably within a year or two, IBM switched within a year or two. I don't know how long it took Nuance to switch. They're not very open. But it turns out that like a bunch of people in the speech recognition community said, yes, we know this. We've been doing this since the early 90s. And actually, even before then, so there's a paper, I'll send Richard the link, but it's called Time Delay Neural Networks, where Jeff Hinton and I think Alex Weibel were doing exactly just a recurrent neural network for phone recognition in like the late 80s. And it looks almost identical to the model I just showed you for how we're doing speech recognition now that everyone got really excited about 5 years ago. Right, so this is a paper from early 90s. This is from people at Berkeley, where what they call MLP, we now call single layer neural networks, most of the multi-layer perceptrons, where they're doing exactly what I just described, right? So they take features, they use their neural net to get targets of which phone do they think is said given the features, and then they integrate that with, they integrate that with their HMM system and do transcription. So back then, they weren't getting amazing results with their neural nets though. So this is a fairly easy speech recognition task by today's standard, but it was kind of one of the benchmark tasks back in the early 90s. And again, MLP is their neural net based system, and CDHMM, that's like a standard Gaussian mixture model based system. And here so these are error rates, so lower is better. Here we see that their neural net system was always worse, but if they mix the two, they get improvements over the best single system. So the question is why, right? Why were people doing this in the early 90s and didn't see great results, and then with very, very similar models with a couple of tweaks, now it's really big news, state of the art, everyone's excited. It's not because people stopped working on neural nets. There were people working on neural nets in speech kind of all along. But kind of what happened was people took some of the ideas around deep neural networks and figured out how to make those ideas work well inside of speech systems. And so I'll talk about those now. So the first big difference is modern systems with neural nets in speech use cnones. Those are those clustered triphone states I was talking about. So in the early 90s and up until people started to see really good gains with deep neural nets, people were using monophone states. So those are the things I described that aren't really good descriptors of speech because there's too much variation in phones. But once you switch and start using triphone states, your system gets much better. And one of the barriers was simply the fact that people didn't think that you could have a neural net classifier with 10,000 dimensional outputs. So they thought the 10,000 way classification task just wouldn't work very well for a neural net. And certainly up until somewhat recently, certainly in the early 90s, a 10,000 way softmax would kill your computer for the types of computers that they have. So that's one, and then I'll talk about more in a second. But just to reiterate, right, so there's a joint paper. I'll send Richard this paper also, and he can put it on your website. But this was a co-authored paper across a bunch of different research groups. So Google, IBM, Microsoft are the big speech research labs. And this is a paper where basically all of them just come together and say, yes, we're confirming when we use neural nets, our systems get better. And this was, I think this came out in 2012. So this is kind of that most recent round of excitement around DNNs. So what's different, right? Why were we doing something in the early 90s? And it wasn't until 2011 that people got really excited and started to see these really good gains. So there's the obvious one, and it would be unfortunate if this was the only reason, that our computers got faster, right? And that's kind of a boring way to improve on your research results. But it's certainly true. And also data sets get bigger, which we all know really helps neural nets more so than other algorithms many times. Other things that happened was people didn't really look at deep neural nets much in the speech community in the 90s. They help a bit. Architecture choices matter a lot, so rectifiers versus sigmoids in particular. Pretraining we thought made a huge difference. It turns out it doesn't. And I think speech was one of the first places where the initial wave of pre-training excitement started to lose momentum. So again, around like 2010, everyone thought, oh, if you want to train a deep neural network, you do this unsupervised pre-training, and then you do fine-tuning, and that's how you get a deep neural network to work. In speech, again, all our data is labeled, and it turns out if you just have a ton of labeled data, you don't really need to pre-train. So if you have a ton of labeled data and start from random network initialization, you actually get within like probably less than a percentage point that you would of performance that you would get by doing unsupervised pre-training. And of course, our models are much bigger, right? That goes on with computers being faster. Yes?
What about label pre-training? Like I was trying to train a speech classifier for people who call in my phone for some service, but I want to pre-train on switchboard beforehand. When you have that much label data online.
Yes. Yes. Yeah. That's a different. Yeah, that's like a slightly different task. So that's more of like a transfer task where you take like a good acoustic model from one domain and adapt it to another domain. That is useful. The other place where that's useful is people look at like low resource multilingual. So like I might not have much labeled data for Cantonese, but I have a lot of labeled data for Mandarin. And so I can train an acoustic model on Mandarin and then try to adapt that for Cantonese. By pre-training doesn't matter. In what I was referring to was specifically for a single task. So like given a bunch of English voice search data, can I get better on English voice search? And the answer seems to be no, not really. So let's quickly go through some of these and just see like concrete results. So depth, right? So this is a nice control experiment from the team at MSR where they just continue adding layers to the network, and then they have this control for what does a one layer 16K. So I think the number of parameters in these match. So like 1 by 3772, I think you end up with the same number of parameters as you do in like 5 by 2K. And what they see is it's kind of diminishing returns where it's much better to go to 2 layers, but once you get past like 5 layers, it doesn't seem to matter. I'll add a warning here, which is that timid is kind of the toys task for speech. Timid is like the MNIST of speech. It's like a really small data set. It's just phone recognition. It's not always a good predictor of performance on a larger task. People had results on timid where they're like, 10 to 15 hidden layers actually improves quite a bit over like 5. But it turns out what seemed to be happening there was with 10 to 15 hidden layers, your optimization algorithm couldn't really find a good local minima. And so it was acting as a regularizer because it just prevents you from overfitting. So more layers is not necessarily increasing your representative capacity in all cases. It might just be stopping you from overfitting because you can't solve the optimization problem. This is some work from my team where we looked at depth on a much larger task. So this is like 2,000 hours of speech. And the different curves here are just different total parameter sizes. So this single curve, we always have 36 million parameters in the network, and we're just changing how we allocate those parameters across layers, and all layers are always the same size. And what we find with all of these is that there's usually a huge jump between shallow or 1 layer and then multiple hidden layers, but it's very, very diminishing returns between like 3 hidden layers and 5, and then from 5 to 7. So yes, depth. So what people were doing in the 90s was always single hidden layer, so that seems like that's a bad idea, but it doesn't seem like we need to kind of do this crazy stuff of 9 hidden layers. Replacing sigmoids. Have you guys seen this by now, that like rectifiers are awesome? No? Yes? Okay, yeah, so rectifiers are awesome. It turns out rectifiers are also awesome in speech. So blue is tanh, red is rectifier, and basically you do nothing except switch your nonlinearity and you just get free performance gains. That's great. What was really interesting here is that a really deep tanh function wasn't performing as well as a much shallower rectifier function. So again, like we have to be careful of this confound that we have, which is we can't optimize our training function properly because it's non-convex. And so when we conclude something about like, a system with more or fewer hidden layers, we always have to be aware that It could just be we're reaching this result because we couldn't optimize our function very well. And the other nice thing here, so MSR worked really, really hard on doing like nice preconditioning of their weight matrices, and I think this was also pre-trained as well. And it turns out if you just take a shallower network and use rectifiers, you get the same performance. So that's great. So convolutional neural networks, they're not used as a default in speech. They're really good for very particular types of speech. So in particular, when we have frequency distortions, so I'm looking at this as frequency that way. So people build convolutional networks that convolve along the frequency axis because our HMM is already, in a sense, sort of convolving over the time axis for us because we're just copying our network and putting it at all points in time. But convolving along the frequency axis is really good when you have things like shortwave radio broadcasts where there's actual frequency distortions. Frequency distortions are not really all that common in speech. It's more common to get additive background noise, but for really noisy environments, convolutional neural networks are good. So let's look back at scaling up, again, trying to explain sort of why is this thing exciting in 2011 that people had been doing in the 90s. So in the 90s, this is a nice plot of scaling up. So they're increasing their training set size and they're increasing their hidden layer size. Unfortunately, these are all single hidden layer networks. So if we think by today's standard, having a single hidden layer of 4,000 hidden units, and that's your whole network, right? That's like really small, right? You could all run that on your phones, probably. But they conclude the right thing, right? I really like this quote, which is, we always get better performance by either using more data or having a bigger neural net. And now we're going to do some crazy stuff and get 8,000 hidden units in our single hidden layer, right? And actually, Dan Jurafsky, who's a professor here in computer science and linguistics, he worked with this group. And so they worked very hard to put neural networks onto not GPUs, but very similar sort of specialized hardware to GPUs. And of course, there was no good programming primitives for those things. So it was a lot of effort to run this 8,000 hidden unit thing that now, again, you can probably run that on your phone. And you can definitely run that on something like CUDA. So this is, again, results from my group, right? So if we look at scaling up, so that work from the 90s, they were all sub 1 million parameters, but they worked really hard, and they knew that if they kept pushing out along this axis, they were getting better performance. And so what we did was we used some of the shared or distributed GPU infrastructure that Adam Coates developed for images, so splitting one model across multiple GPUs. And we're able to push out to like 400 million parameters. We actually pushed out to 1 billion, but it doesn't help. And we can just run a much larger version of this experiment, which is, if you believe that all you need to improve speech results is a bigger model, then we can give you bigger models. Turns out that, so this is frame error rate. So this is how well am I doing just on the classification task of, given some audio features, am I telling you the correct state, yes or no? And then I have to run it through my overall system to get word error rate. So you get some gains, but again, the gains are somewhat diminishing, which is why I said, so going out to like 1 billion doesn't really help. But it's nice to see that, if your data set's large enough, yes, keep making your neural net bigger, and results improve. You probably wouldn't run a 400 million parameter model on like a Google Cloud ASR system for now, because they don't want to put GPUs on like everyone's Android speech recognition backend. It's very expensive. But eventually, right, models will just keep getting bigger. Yes?
To what degree, so you mentioned before that difficulty of optimization is sort of a lurking background variable in a lot of these results. To what degree do you think that the limitation
applications that are being run up against at bigger parameter sizes are sort of a factor of optimization, or versus like just intuitively, do you have an opinion?
Yeah, so we've done some extra analysis. Actually, Peng did a bunch of extra analysis on this as well, where we try to look at when we have layers that are that large, one thing that can happen is you end up with units that don't ever activate, or they activate only very rarely because basically you're not fitting the function well enough. And so you can look at per unit or as a layer overall, how am I kind of distributing the encoding task? And if I see that that distribution is somewhat flat, I at least know that I'm taking advantage of those parameters. I don't have a good sense for whether I'm anywhere close to optimally taking advantage of those parameters. So like what I think is a really nice theoretical result for neural nets that has yet to be achieved is doing something like estimating the dual gap. Basically, if you can tell me, given some model, what is the best I could possibly do on a task, and then I have some sense for whether my optimization algorithm is going to get me anywhere close. So like for most convex problems, you can do this thing where you can tell me F star, like the best possible you could do on it, without having to tell me anything of how to achieve it or what that model would look like. I think that would be a really nice check to have for neural nets. Okay, so just to review and wrap up the HMM DNN stuff. So they're awesome. They're used everywhere. Your phone uses them more than likely. It seems to be the case that some mixture of having more data, having faster computers, and knowing how to train deep neural networks is what led us to this thing that was a breakthrough in 2011 that in hindsight it's kind of weird that it was a breakthrough because people were working on very similar models for such a long time. But we kind of understand why in speech the people who were working on it before weren't seeing as nice of gains as we saw when kind of more neural net centric approaches were taken. And now I'm going to talk about a model that tries to get rid of this whole HMM thing and move us toward basically pure neural net based speech recognition, which would be very cool. So this is the model that we've been talking about so far, right? So the problematic piece and the why these things are like 20,000 lines of code is all up here. It's because I take words, I have to break them into these funny things called cenones because phonemes aren't sufficiently granular. And then I have this HMM infrastructure that's kind of imposes these logic constraints on what I'm allowed to transition through and those types of things. The neural net component of these systems is actually relatively small. Like it's a neural net classifier, right? It's like 100 lines of Python code. But it's everything else. And along with this, outside of just the model that I haven't talked about at all, is doing the decoding task. So this is one part of the decoding task. The other part of the decoding task is a language model. You guys have seen language models already. And yes, people do use recurrent neural net language models for speech, and they see some improvements. But the search problem is fairly large because I'm searching through the space of all possible sentences. I have to deal with these constraints of kind of taking a hypothesis sentence and mapping that to a sequence of states, and then I can score that sequence of states with my neural net. But doing that search efficiently is like kind of its own research subfield. And people have made a lot of progress on those, but they're still very large and unwieldy infrastructures to do that decoding task. So about this time last year, Alex Graves and Navdeep Jaitley proposed something very radically different. And they basically just said, we really like neural nets, but we really hate all of this messy infrastructure and all these linguistic assumptions. Let's try to do something where the neural net is just kind of doing it all. And so what they proposed was, so given a transcription, I'm going to ignore the notion of phonemes, and I'm just going to convert a word into characters, right? This is a very easy conversion to make. And I'm going to allow my model to do two things. I'm going to allow it to output the same character multiple times, and if it does that, I just collapse multiple characters into one. And I'm going to introduce a symbol that here is denoted as underscore, which really means kind of blank or junk. And that's the way that the model expresses that for this point in time, I just don't want to output any type of character. So we have a neural net, and in their case, they were using LSTMs, but we have, we can use whatever neural net we want. Turns out that it needs to be a recurrent net for it to work well. But we just output a distribution over characters at every point in time. And then the simplest version of decoding these things is just argmax decoding. So I just say the most likely character at this frame or this point in time is S, another S, and then a blank. And then I apply this collapsing function. The collapsing function just throws away all the blanks, collapses all the duplicate characters, and that's how I get my hypothesis transcription. Looking at this loss, so that's the model, and then we need to be able to train this model. So to train this model, with any speech system, what we want to do is maximize the probability of the correct transcription. And here the correct transcription is Y, and then because of their collapsing function, there are many pre-collapsed strings that map to the same post-collapse string, right? So here's a simple example where the output label is AB, and I have 3 time steps. So here are like all permutations of, including blank in between the two, including duplicates of A, including duplicates of B, and so on. So if I want the maximum likelihood, if I want to maximize the likelihood of the correct utterance given the input features, I need to sum over all possible time level labelings, and that's what this B inverse thing is. This is just the mapping function. And so the probability of the final transcription is the sum over all possible consistent time level labelings, and then the probability of a given time level labeling is just the product of all frames in that labeling. So I'm assuming that my output at each point in time is independent given the model and the entire utterance features, and then I'm just summing over these things. And I can compute this sum exactly using dynamic programming. Questions about that? It's kind of hard to see. Yeah.
Is it really true they're conditionally independent, though?
They're conditionally independent because I condition on everything. So X here is my entire utterance. So like in a recurrent network, it's the same concept as like a CRF, right? A CRF assumes that outputs are conditionally independent, but since you're not modeling relationships between the things you're conditioning on, you just condition on everything. So like conditioned on everything, sure, I think it's not that bad of an assumption. Other questions? No, okay. So that's the math, but it turns out this thing works, which is really interesting. So this is an example. This was Ani Hannon and I just re-implemented this model and ran it on Wall Street Journal, which is people reading news articles aloud. So pre-collapsed, you get a whole lot of blanks because utterances they tend to be much longer in time than characters you're saying, right? Because we're recording features about every 10 milliseconds, and so it's hard to like spit out loads and loads of characters that fast. So for most of the time, you're not saying anything, and then the model decides to output single characters. So again, this is our per frame string, and then we just apply that simple collapsing function. We get something that looks like this, and if we compare that to the reference transcript, it's actually not that bad, right? It makes mistakes, but it makes mistakes in ways that are almost more interesting than typical speech systems. So this doesn't have any sort of lexicon in that, like, blueprints is not a word, but the system doesn't know that words exist, so it doesn't care. Whereas in a normal speech system, and probably if you use like Android dictation or something like that, when it messes up, it'll output some other word that might be vaguely phonetically similar, but is very different semantically, and so that really screws up like your email or text message or whatever. Here, the system doesn't really know what it's supposed to be saying, but it outputs something that if you kind of read it, it just looks like someone doesn't know how to spell or they never learned English properly. And along with that, just initial rounds of experiments on this kind of smaller corpus, which is people reading news articles, we looked at what happens if you don't have any recurrence in this model. So now we're looking at character error rate. So instead of words, I'm just outputting. I'm not forcing you to output words because word error rates are bad. If this model, right, if we get blueprints, which is only one character off, that's still a huge penalty from a word error rate perspective. So instead, we're just looking at string edit distance for characters. So deep neural net compared to a forwardly recurrent neural net, yes, recurrence actually really, really matters. And it turns out that bidirectional recurrence is actually really important for these models. So being able to pass information both forwards in time and backwards in time is much, much better than just one direction, and is also much, much better than a model that, even if you make the feature windows very large and overlapping, it seems like you have to be passing information about the hidden state of the network along in time to get good performance. So this thing just outputs characters, but ideally we want to use a language model. So language models really, really help speech recognition systems overall. So we output, we get character probabilities, and then we set up this search task, which is a pretty tricky search task, it turns out, because we have our language model and our search algorithm operating in the space of words, and then we have a model that's outputting characters, and so we need to sort of figure out character probabilities that are consistent with words. So you can set this up, but it turns out that the way that this was implemented, it would be fairly non-trivial for us to use anything beyond like a bigram model, because it impacts sort of how your search algorithm has to look backwards and forwards in time. But again, so fairly small improvements in character error rate between so a lexicon is simpler than a unigram language model. A lexicon is just saying this word exists, and you're only allowed to say words that exist. Bigram is a standard n-gram bigram language model. But this is hugely important for word error rates, right? Obviously, the jump from I'm outputting a bunch of characters, but I don't know what words are, to I'm only allowed to say words improves your word error rate a lot. And likewise, a bigram language model improves a lot. This isn't a completely fair comparison, but this is comparing our model, which is a vanilla deep bidirectional recurrent network, versus the Graves and Jaitley model, which was it's a BLSTM, it's a bidirectional LSTM. So it's implemented by different groups, but this can give us some sense for, are LSTMs really that much better than recurrent nets for this task? Seems like they're a little better, but not tremendously so. And likewise for word error rates. So for word error rates, actually the improvement once you impose a lexicon, almost vanishes completely. And take this with a grain of salt, because we were the RNN model was performing a harder task. So what they were doing was they had a state-of-the-art speech system dump out what's called a lattice, which is like a set of possible transcriptions, and then they use their LSTM model with a language model to just rescore hypotheses in that lattice, whereas our decoding algorithm was just from scratch searching through the space of all possible transcriptions. So that's a somewhat harder task, and that might explain some of this performance gap. But nonetheless, I think it's interesting. I personally, I haven't seen good evidence for BLSTMs as being like very directly compared with RNNs and sort of explaining why or demonstrating that they work so well. I'm being careful not to bash them because I know I'm on video. So that's great. So Graves and Japley came up with this model that got rid of, 10,000 lines of HMM infrastructure that we've been using to do speech recognition for the past 25 years at least. But there's this pesky thing that came along with it, which was the model's reasoning it entirely at the character level, and yet we're still doing language modeling at the word level, which means we have to sort of take this model that can do all these interesting things like invent new words. If it hears me say a new word, because it's just reasoning about characters and not constrained to a lexicon, it can just say, oh, I think you said this word, I've never heard it before. But all of those gains go away in decoding because we're decoding using words. So, right, out of vocabulary words, right? So when there's a new political party in Greece, or a new slang term, or a big one that happens in speech system are word fragments. So I'll say part of a word and stop and say something else. These really mess up speech systems because it's not very tractable to have all possible fragments of all possible words in your lexicon or in your dictionary. That's just a lot of stuff, right? Especially we already have 1 million words. Now if we want 1 million words plus, their front half, their back half, and permutations thereof, that's really messy. So some work I did with Xiang Zhe here said, let's just get rid of language models and replace that with a character language model. So our model's reasoning from audio to characters. So instead of reasoning about these word tokens, let's reason about just characters. So a character language model you can do with a recurrent neural net, and we did that. It turns out the recurrent net works better. But this was the intuition of just do all of your reasoning entirely at the character level, forget about words. Turns out this works. So we did this on Switchboard. Switchboard's interesting because it's people talking to other people, and so there's lots of those natural variation and word fragments and things. There's not too many invented words on Switchboard, but it's a good start at least. So in HMM, GMM system, right, that's our standard baseline. That's how speech systems have worked for a long time. If we use no language model and just have our thing that goes from acoustics to characters with no other information, really bad. This is word error rate performance now, by the way. This is a 7-gram standard n-gram language model, but over characters. And it turns out that 7 grams is about as large as we could push the model. So your symbol set for characters is only something like 40, but still it's difficult to make really high order n-gram models using like a standard n-gram modeling toolkits. I think this 7-gram model is already several gigabytes. But we could get actually better performance with a neural net language model. I think our neural net here looks at a history of 19 characters. So one of the nice things that you guys probably already talked about with neural net language models is you can have like infinite context. Here we didn't use. No, I guess this is a recurrent net. So I guess in theory we also have like infinite context. Yeah. Oh, you're stretching. Sorry. And of course, HMM, DNM models, they're a little bit out of our reach. But again, from this system to this system has something like 20,000 lines of code. This system has something like 300 lines of code. So that's a very nice reduction in complexity. And this system is the first time that people have taken, so this is 2 neural networks, right? This is a neural network from audio to characters and a neural network from characters to characters for your language model. And then a pretty easy to implement just decoding standard beam search algorithm. And we're within striking distance of the baseline standard speech systems, and I think well on our way to state of the art. And because we're reasoning at the character level, we can do really interesting things, like we can transcribe words that the model has never seen before. So in italics here, so this is reference transcription. The word fidelity is not in our vocabulary for this system. So our HMM-based system, it's not allowed to invent new words, and so it does what standard speech recognizers do. It like injects weird words so that it sounds roughly similar, but we've totally screwed up the semantics here, right? Like this data was recorded in the 90s, so Fidel Castro was one of the topics. But here, right, our character-based system just invents the word fidelity. It puts an on there for some reason, but it invented the word fidelity, so that's really cool. And again, here's a case where it invents barometer, which is cool. It still screws up the utterance, right? So I'm not claiming that it's perfect all the time, but I would claim that if I show this to you and I show that to you, you will find this one somewhat easier to interpret. Finally, this is this notion of disfluencies. So said I'm and then switched what they were saying. In standard speech recognition systems, disfluencies really hurt us because we don't know whether they're supposed to be a silence or whether they're supposed to be a word, and we don't really have this notion of word fragments in our lexicon. So we inject something reasonable. Here the model, the character-based model just came up with a fragment. If you want to see a standard speech system inventing words like that, take out your phone and do like email transcription or something with voice and just blow into the microphone and it'll say something, right? It says, oh, I hear speech, but I have no idea what it is. So I'm just going to start sampling from my language model. And depending on like how you blow and those types of things, you'll get different words. Usually they're words with like lots of F's or S's in it because it's like, right? It hears that in the microphone. Yeah.
Hey, can you go back to when you're conditioning on the characters? Like, where do you get the set of things to condition on?
This?
So what is the set to condition on? Like, how did you get? Oh yeah. Like, how did you get those 3-6 characters?
Oh, so
It is not from a lexicon.
it's integrated via like a standard beam search. So in beam search, you might seed it from like the argmax of this model, and then you search around. So beam like it's standard, just like incremental beam search of you look at the probability for next character in the acoustic model, and then you weight that by for this sample in my beam, what's the context? So this would be in a beam search, you maintain a set of hypotheses. So this is the context for one hypothesis.
But that's never like extremely large. Like that set of things that you're. Like how big is that?
It's like the length of the transcription.
Okay.
So-
which is like just 1, 2, 3, 4, 5, 6.
Yeah. Yeah, I guess to give you a sense, so for switchboard, I think the mean utterance length might be something like 400 frames or something like that. So our beam search is slow. Like I think to decode our test set, which is only a couple hours of data, it probably takes us like overnight, or somewhere between a couple hours and overnight, depending on how large your beams are in that search procedure. But that's something that like there's lots of research in making beam search really fast. Like you can just reuse a lot of the parsing literature. We just took like the simplest possible algorithm and did it that way.
Okay. But it's like not real time though. You wouldn't be able to do this like.
No, ours isn't real time. But again, that's something that you could make it real time. You just need someone who's an expert in how those decoders work, and we're not. Yeah, so we just wrote the simple version of the decoder. So like the fast real-time speech systems today, the standard tool to use is finite state transducers. So you'll take your language model and make it into a finite state transducer so that when a new utterance comes in, you're very efficient, because you can do like very efficient graph manipulation with finite state transducers. So we could do all that stuff for our model, but we didn't yet. So yeah, we get out of vocabulary words, and finally I just wanted to look at some interesting properties that this model just kind of learns on its own or sort of falls out of the model. So this is what our character probabilities look like over time. So I'm just showing you the character of that junk symbol versus any other character. So this is the sum of all non-junk probabilities. And then this is the argmax transcription and the post-collapsing transcription. So one thing we see that's weird, or just a property of these systems, is that they tend to spike. So it'll say blank with very high confidence almost all of the time, and then all of a sudden it'll say, oh, I saw this character, and then it'll turn back off and say, nope, I'm very confident that there's nothing going on right now. And if we compare that to how standard HMM-based speech systems work, it's like the exact opposite in many ways. So in a standard speech-based system, in a standard speech system, because it's a generative model, I want to have high probability for each phone for the entire duration that that phone is being spoken. So I never have this notion of like, I'm not hearing anything now, I don't need to output anything. I'm always trying to just have this nice generative model of like when phonemes occur over time. And this causes problems. We know that this causes problems for HMM-based systems because, as I said, like your tongue has mass, and therefore there are dynamics between saying one phone followed by another. So it's always at the boundaries that phones are most difficult to distinguish. But this model, we're trying to force this model to get the boundaries right, when for just speech recognition, we might be totally fine with ignoring those really confusing boundaries and just spiking when we're sure that we've heard the phone or character. So that's one difference. Another difference is we can look at how this thing learns to align data. So in a standard speech system, I very carefully build that system up over time such that, so when I train a system, I have the word level transcriptions, but I don't know when words occur during the utterance. And so I do this careful EM algorithm to essentially come up with alignments of words to time so that I can keep training my system and have it be consistent. And in the CTC-based model or in the kind of pure neural net-based model, we don't do that. In the pure neural net-based model, we just say, here's a bunch of audio files. Here are the sentences that you're supposed to output given those audio files. And in the beginning of training, I'm telling you nothing about when those words occur in the audio file. And then after we trained a model, we can go back and look at the character output by the model synced up to alignments that are produced by an HMM system. So this is for the phoneme k, right? Those are like cat, car, those are all k. I align all instances of the phoneme k in my, I think this is training data. I align all of those to start at time 0. And now I'm looking at the average probabilities of my CTC character model averaged across all of those instances. And this dotted line here, that's the average duration of k. So in an HMM-based model, you would see high probability from 0 to the dotted line, roughly, because again, it's this generative model. In the CTC-based model, it tends to spike only right at the very beginning, or there's this other mode which has it spiking towards the end. We think that the very beginning, those are times when k is probably a word initial or syllable initial plosive, so like car, cat, those types of words. And then you get this other mode for when k is occurring in the interior of a word. And so it might be ignoring some of the context because it's confusing and waiting until it's more confident to output that phone. So we can repeat this analysis for a bunch of different phones, and we see that the neural net model is learning to behave in different ways for different phones, and it seems related to what types of sounds are happening. So sh, right? Sh, the model again is sometimes going to happen, sometimes going to output those characters very early, and we can see it's outputting the S and then the H in rapid sequence. Sh is interesting because it also happens in like shun, like Dick Shun, T-I-O-N. And for those things, there's a different mode. Again, it seems to be the difference of like being word initial versus happening in the interior of a word. And then, so wa is a glide, and it seems like it happens a little bit later. The reason for that, we think from a linguistic perspective, is that things like glides, they tend to be much more affected by the phonemes before them. And so you probably have to wait to be very confident that you heard a w and it wasn't something else. And then for vowels, again, we're outputting them very early and then going silent. Although for vowels, it seems like you output them slightly later than you do for k. And again, it's the hypothesis as to why is because vowels are much more affected by their context than things like k, consonants generally. I'm over time, so I'll just quickly conclude, say neural nets are really useful in speech. They're running on your phones right now, very likely. We have a pretty good sense of why kind of the modern incarnation of DNNs is interesting, whereas they were not necessarily the most competitive models for speech throughout history. And then the most recent stuff I showed you is, I think in 5 to 10 years, your phone won't be using an HMM at all. It'll be using purely neural net language models and neural net audio to character or something like that models. So yeah, that's all. Thanks. And I'll send Richard a couple papers, and these slides will be online.
I guess they're kind of related, which is like, couldn't you do all the CTC stuff with a vocabulary of phones?
Yes, yes.
Has that been tried, or?
I would guess that someone is trying it now, but I don't know who. The characters just makes decoding super, super simple because you don't need a pronunciation lexicon. Yeah, someone should try it with phones. Yes.
I guess I guess the other question is like, and it's sort of related to this, is for some languages like Chinese, obviously the smallest units of orthography are like probably too big, I guess, to directly apply this technique, and maybe you would want some sort of.
Well, they're like syllables or something,
Okay.
right? Or
But they're very contextual.
yeah, I don't know. I don't know. Ask Peng. He knows CTC and he knows Chinese. Yes.
I guess the sort of the other like sort of next step, which is obvious enough that everyone is probably doing already, is like how can we cut out this like intermediate representation? How can we build a end-to-end neural network trainable system? Are there like
Yes.
issues that you run into when you start to do that?
So I didn't talk about it in this talk, but the other thing that I think makes the CTC-based recognition systems really interesting is they're very compact, and you're directly optimizing for transcription with like a machine learning loss function that you can easily write down and optimize. So that means if I want to use like a question answering system or a dialogue system that has transcription as a component, I can now do something like multitask learning, where I'm now training my recurrent neural network both to do transcription, but also to like predict dialogue acts directly. People should work on that. Yeah. Yes.
How does it handle the case where like there's multiple characters in a row in a word?
Yeah, so like with shun, it does this, and you can see with SH too. So SH, this is a phone, sh, that in English usually corresponds to either SH or TIO, and it outputs those things in very rapid sequence. So essentially what seems to be happening is the network hears that sound, and it says, I need to output these 2 units in response to that sound, and so it just does them one frame after the other and then turns back off.
I mean like glass, SS.
Oh yeah, that's similar to SH. Oh well, glass.
No, I mean the decoder, like you said, it combined letters that were repeated. So like.
Oh yeah, but if I output S blank S, I'll output 2 S's.
You combine the letters, then get rid of the spaces, not spaces, then letters.
Correct. Yes. Yeah. Sorry. Yeah. You collapse duplicate letters and then blanks.
Okay.
Yeah.
It just seems like there's lots of letter like words with.
Oh yeah. You can. It has no trouble that I've seen outputting like repeated letters like glass.
Okay.
I thought you were asking about single sounds that map to multiple letters,
No,
and for those it does that.
The way it's decoding, it didn't seem to do.
Oh, okay. Yeah. Yep. Other questions? Oh yeah.
I don't know. You didn't really talk about punctuation. Like if you're like a question mark or an exclamation point.
Punctuation doesn't exist in speech, so we don't care.
So if I like, scream something, there's like no inclination, or if I raise it up at the end, there's like
Yeah. That's not in our standard transcription tasks. So like switchboard has no punctuation. You'll see punctuation marks, but those are transcriber notes essentially of like, they'll put fragments in parentheses and that kind of stuff. But like spoken speech has no punctuation, and so then our transcriptionists don't put any in.
And then, do you have any intuition why you're not hopeful for LSTMs for this task?
Oh, I mean, there's an existence proof that LSTMs work just fine for this task. I have yet to see a paper that does good control experiments on a real task that says, here's how an LSTM performs, here's how an RNN performs, and yes, the LNN is the LSTM is way better. What I've seen are people set up tasks with sort of like their toy tasks with sort of arbitrarily imposed very long distance temporal dependencies, and then they show that LSTMs are better. And yes, I'm willing to believe that, but I'm not sure that this task necessarily demands very long range temporal dependencies. We could say that they exist in theory, but I haven't, I don't know. I want to see a real problem where an LSTM is like twice as good as an RNN, and then I'll be convinced. Yeah.
So how does this model know where to put, say, silent characters, like the H's at the end of O and yeah? Is that just all the language model thing?
Yeah. it learns it from the data that certain sounds just correspond to like multiple, like just tokens of multiple characters. But then to get spelling right, so you saw in like, in the examples I showed where we didn't have a character level language model, it outputs like blueprints instead of blueprints, because that's probably the way the person pronounced it. So that's why we need our character language model, is to like learn how to spell. Yeah. All right. Thank you.